Hello, everyone. Welcome to MACSMIN 2025. It's a great pleasure to introduce Professor Simon Billinge from Columbia University. So, Simon, you could comment about what you wish yourself.
I will, don't worry.
So Simon will talk. We'll talk about very important questions. When is a structure a new structure, for example? So over to you, Simon. Yes.
Yeah, thanks so much, Vitaly. So it's such a pleasure to be part of the MACSMIN family, and I really feel honored to get invited back. I'm not sure, like each year I feel incrementally less my contributions, but I love this community and I love being part of it. So thanks, Vitaly. I'm sorry I can't be there this year. This coincides right with the beginning of the semester and some other things I'll just bring up in a second, and so it's extremely busy. So I also have to, mea culpa, I saw the wonderful slate of talks and there's about 90% of them, maybe all of them except my own, that I want to see. And I haven't been able to catch them just for the same reason, so let me explain that. So yeah, when is a structure a new structure, and then towards new measures of structural similarity. So how do I do page down? I may have to. Okay, we're there. So as Vitaly said, I'm at Columbia University, and I would always start my talks showing a picture of Manhattan, looking south, and there's a green region to the left and a green region to the right. These are the city parks, and then there's another green region here, which is Columbia University. That's the campus. And then I always joke that this yellow circle here is my proposal to build a synchrotron in Manhattan, and that I've asked the mayor to engage in this project, but he hasn't done it yet. But there's actually some news and update, which is that actually starting in January, I'm going to be moving to Santa Barbara. So my new introductory slide is going to look like this. This is actually a picture of the UC Santa Barbara campus. So it's a little bit of a lifestyle change from this to this, but I'm looking forward to it. It's an exciting opportunity. UC Santa Barbara has a very, very strong materials program, and they have also a state-funded Center for Nanoscale Nanosystems Institute, California Nanosystems Institute, which I'll be heading up over there as well. So yeah, I feel to complete everything, I ought to actually propose to the Santa Barbara folks to build a synchrotron in Santa Barbara. So when that project is actually underway, this is what the synchrotron will look like in Santa Barbara. But of course, I'm joking about that. When we do synchrotron experiments, we go to DOE facilities. So this bottom one is a picture of Brookhaven National Lab. So for those of you who don't know me and my work, I'm coming from an experimental end of things towards the applied math end of things. And we specialize in studying local structure of nanomaterials. Over the years, we've done this and developed techniques and methodologies for doing that. I'm not going to talk about that today because we're talking about a different topic. So the way I wanted to frame my topic was actually to look at materials discovery. So this is a big bananas at the moment. People want to discover new materials. Why do people want to discover new materials? It's in the context of technology, basically. So a goal might be to make a better battery or to discover new drugs. Strictly, that would be called drug discovery, but since drugs are made of atoms and materials are made of atoms, a drug is kind of like a material. If you want to make a new kind of touch-sensitive screen for a mobile phone or a new computer, or if you want to make a self-driving car, these are all technologies that are kind of revolutioning our lives, especially in the last decade. I would say it's kind of accelerating. In order to do that, you need new materials that are suited to purpose. And so I'll talk a little bit more about that. So how did people discover materials in the old days? So basically, we learned physics and we learned chemistry. The traditional approach was you learn the basic sciences, and that gives you enough kind of knowledge to make intelligent predictions about what a new material would be. And then when you get close to a new material, you just use trial and error, some kind of Edisonian approach. So one example is lithium-ion batteries. And they received Nobel Prize in chemistry in 2019. So Akira Yoshino on the right, he actually developed a way of capturing the lithium and the anode side in disordered carbon. Stanley Whittingham made the first lithium-ion battery, but it was a kind of not very good battery made out of sulfides of transition metals. And then John Goodenough on the left figured out that actually he was a physicist, but also a solid state chemist. So he straddled those two fields, and he had the insight that you could get a larger voltage and a more stable material if you made a transition metal oxide cathode with lithium in it. And he developed back then lithium cobalt oxide. You can say he discovered it. I mean, it was a material that nature made, but he discovered it in the context of lithium-ion batteries. And that's in a large proportion of modern lithium-ion batteries at this point. They have lithium cobalt oxide in the cathode side, and they have a disordered carbon anode. And so there's new technologies emerging now, but basically in the old days, this is how you did it. What the proposition is now, though, that we have AI, right? We have ChatGPT. Like, let's have ChatGPT discover all our new materials for us. So we'll do AI accelerated materials discovery. And the basic proposition is that you're going to make these deep neural nets and you're going to train them on large databases of known materials. And then we'll develop ways of accelerating the discovery of new materials. And so some recent examples are DeepMind's Genome, Microsoft's MataGen, and Meta's Ecoformer, and they recently published this OMAT24 database. So I'm going to say a little bit about each of these things. What's kind of interesting to me here is that in the old days, we were doing this kind of basic science research in academia, in the universities, and we were getting grants from the federal government to do this. What DeepMind comes from Google, and what Google was doing was search engines. Microsoft was doing software, and then it was doing search engines. Meta was doing social media. So these guys all decided that they all want to become like materials companies now. So they see value in actually predicting new materials. So all of these tech companies all want to become materials companies now, which I think is kind of droll, kind of interesting. And it has a big effect on our work, as I'll allude to shortly. Okay, what was the traditional approach and how well did it work? So let's play a game. We'll play traditional versus AI, and we'll go through a few different technologies and see what happens. Current commercial batteries. We've already discussed this. That was won by traditional. All of the materials to my knowledge, all the materials in current commercial batteries were found by traditional methods. Computer chips, pretty cool kind of thing. You can have this kind of multi-layer integrated circuits. It's a real amazing kind of materials problem, traditional. How about touch-sensitive screens on our phones? They came around fairly recently. How about those? Actually, those materials were found by traditional methods. What about self-driving cars? They have a bunch of sensors in, right? They have to be able to detect light, and they detect kind of radar beams, and I don't know what they detect, and they have the computers to do it. They're all made out of materials that were discovered traditionally. So let's be clear that well, here's another one which is slightly arguable. How about biodegradable plastic? And the joke here is that actually, I think the biodegradable plastics are terrible, and this is a kind of a massive failure of material science. But nonetheless, the ones that we have were found by the traditional method. So actually, traditional methods, let's be clear, they're good. That's a good way of discovering materials. And in fact, I'm not really aware of any meaningful technology that's actually in production that uses an AI discovered material. But look, it's early days, so let's explore this a little bit. So how does AI accelerate this materials discovery work? So this is actually a snapshot of the materials prediction world circa 2019. So this is 6 years ago. And this is a review paper. It was in Nature Reviews. And on the right, I'll mention some of the things on the right. But basically, a statement of the problem is that we have the periodic table of the elements, and arguably there's 213 of them. Actually, there's only 92 so that are naturally occurring, and some of them only survive for microseconds, but doesn't matter. Roughly speaking, there's kind of 100 of them. Did I say 200? Yeah, there's roughly 100 of them. And if you just do the combinatorics, there's 7,000 possible binaries in principle. There's 270,000 possible ternaries, and then there's 194 million possible quaternaries. These are just simply doing combinatorics on those elements. I'm not sure if they put constraints on that you have to mix cations with anions, or they just probably do a dumb counting. And then how many of those in this, again, circa 2019, how many of those were actually known materials? And that's a hard job to look at the literature and get those numbers, but these are the numbers they quoted. So 72% of binaries were known. In other words, there are 0.72 times 7,000. These are the number of known binaries. It goes down to 16% for the ternaries and 0.6% of the quaternaries. So clearly, like the big design space is when you get to more complex materials, the opportunities for new materials. Back then, the computational approaches people were using were basically just kind of global search algorithms. Most of the advanced stuff at the time was being done with evolutionary algorithms and just random sampling guided by some kind of global optimizer. And you always want to find, and it's easy to generate a random arrangement of atoms. It's much harder to find that how those atoms would arrange in a way that's stable, chemically stable. The way that you compute the formation energy is using DFT, density functional theory, which is a quantum mechanical theory applied to materials. And so basically these algorithms were doing random sampling plus DFT, but they were doing it in a slightly smart way. Obviously, if you just completely randomly sample such a large space, the probability of finding stable compounds is low. And then on the right, these are actually pictures from that paper. This top left one with all the red color, I don't have a pointer and what's this? Oh, I can, okay, yeah, I can draw. Okay, so this guy here is, I don't like that pink though. Let's do this green. So this shows actually the free energy as a function. It says order parameters, but it basically means different order parameters include the chemistry and the geometry. And they wanted to make the point there's some global minimum in here somewhere, but you actually the most of the kind of stable stuff all exists in a certain small region of this parameter space. Another thing that they point out is actually, again, this is these are nanoclusters of silicon and oxygen, and you see that they call it islands of stability in a sea of instability, and so these little islands of stability emerge out of the sea of instability. But there tends to be, it looks almost like the drip line in nuclear physics, where you actually, this ratio of M to N, which is silicon to oxygen ratio, there's lines of stability that follow these straight lines here. So these are some little bit of understanding that's emerging. But then the other thing is that you can do now looking over here, we can do large surveys of many compounds. This was actually property-based, so they were looking for superconductors. And this is something that will warm Vitaly's heart, because he loves these kind of maps. But this is just they call it materials cartography. This is basically looking at possible compounds in some low-dimensional space that looks like a map and trying to infer like something useful from it. So all this was already happening in 2019 using kind of more or less conventional methods. Okay. All right, now I have to get rid of that. Okay. So I said that I didn't know of any computationally determined materials that were in production, and that's indeed true. But of course, these guys were trying to promote their work and their field. And so this is a table from that Nature Reviews paper where they're showing, oh, in this year here, we discovered this material, and this is something about the material, and here's the reference. But it's all kind of we discovered a new material. Oh, we discovered a new material, but not, and some of them are nominally have like interesting properties. This one is super hard and so on. So, they're kind of claiming success, and that's great. Here's the second page of this table. So yeah, like you can actually predict materials that weren't previously known, and then people can go and do experiments and find those materials. But if you remember back to our game of traditional versus AI, it's really the ones that actually make it into production, there's not so many. So what about post 2019? What's happening now? And this is where these tech companies are getting involved. So this was the first one of the three that I mentioned. This is actually DeepMind, which is part of Google. And they were using a deep neural net to do this thing. But it still looked actually kind of like the global optimization one. They're basically encoding information about the materials in large GNNs, graph neural networks. They have, I'm not an expert on this, so I don't really, don't ask me questions about this, but it looks like their architecture is something like they can generate structures. This is a known structure. Oh, let me get this thing again. Okay, so this is a known structure from a database. Then they do some random substitutions of different elements. They train a graph neural net in some way that captures this geometry. In other words, the spatial relationship of these atoms. Then at the same time, they do a thing where they just capture the chemistry in a graph neural net. And then they train that. And then, so this one has the chemistry, this top one has the structure, and then they shove it into DFT somehow or other. And the DFT can do some local minimization. Hopefully they've made a prediction that's close to it. And they used some kind of adaptive learning here. So initial guesses were low probability, but because they were learning the GNN weights, as time went on, they added this back into the input information. This is this feedback loop here. Then they were getting much, much higher hit rates. In the end, they had to run DFT to figure out what was actually stable. But, here's a bunch of materials that they predicted that presumably weren't. And I know Vitaly has a lot to say about this, and so do all of the chemists. There's a lot of skepticism about it. But the interesting thing is that actually they came up with what they nominally thought was a database with 4 million structures in. How big a number is 4 million? Well, it's big compared to the database of known structures, which is, if you do just in organics, it's hundreds of thousands, like 500,000 structures, something like that. So 4 million is big compared to that, but it's kind of small compared to 100 million, which is the possible number of quaternaries. And here they're doing obviously more than quaternary. This is a quinternary. So now we have a database with 4 million nominally stable structures. So that's Google's DeepMind, and that was 2023, I think, 2024. So these guys all want to get in on the act. Meta, which is the company that has Facebook, they're also doing something very similar. They're also doing high throughput searches, combinatorial searches with a DFT minimization. And what these guys can bring to the table is a massive amount of compute. So they actually came up with 118 million structures. So they're getting close to the total number of structures allowed for quaternaries. But according to their paper, they used 400 million hours of CPU time. So if you ran their model on a single core, it would take 45,000 years. So if they started the work and finished it now, when they started the work, the humans would still be cohabiting with Neanderthals. That's how big the compute is. And obviously they can do that because they're very, very rich. There's no way that we could do this in academia. So that's another kind of interesting aspect. So both of those are very high throughput combinatorial approaches to discovering new materials. There's actually an interesting development which came from their great nemesis, which is Microsoft. And Microsoft has actually built a generative AI model, which is considered to be a foundation model. So like GPT-3, GPT-4 are considered like foundation models for language. These guys have produced something they consider to be a foundation model for predicting materials. And so they don't actually give you a large database of materials. They give you this model, and you can actually use this to predict your own materials by giving it some kind of conditioning vector. So I'll talk a bit more about this too, because this is work that we did in my group on structure prediction, which is closely related to this Microsoft MataGen model. But the big difference is that we were using kind of laptops and PCs and little tiny clusters at the university, and they were doing some huge compute on, they had like more than an order of magnitude more structures in their training set than we did. But I'll come back to this because it's kind of, I think, an interesting story. So that's where we are then. All of these papers, this one says 2023, but this is actually V2, their second version, which came out only this last year. So their V1 wasn't quite as powerful. So all of this has really taken place in the last 2 years. So we're really on the kind of cusp cutting edge of this kind of AI accelerated materials prediction. So now I want to just kind of delve into this and actually show you a little bit of a personal journey that I've taken to get here. Like I told you, I'm coming from experiment, and I'm not a mathematician. I'm not a computer scientist. So the first thing that I wanted to do was I wanted to learn about materials. I wanted to learn about materials using AI. So that was my objective. So what I'd like to give a talk about is what I learned about materials from AI. But before I do that, I need to give a little side story, which is what I learned about AI from my studies of materials, because this was actually a bit of a journey. So because it's a journey and because we love maps, this is just a Google map. And I was making this slide and I was like, okay, I could just make it a text slide, or I could have some nice pretty picture on it. Let's do a Google map for a pretty picture. So what should I choose for my Google map? So actually, of course, I chose Monaco and Monte Carlo in honor of this great metropolis algorithm that we all love, that we all know and love, but none of us use because it's too inefficient. So anyway, let me recap my journey. So the first thing was, I'm like, okay, this machine learning sounds pretty cool. What does it do? Well, it does cats and dogs, right? It does categorization. You take images of cats and you tell it it's a cat. You take images of dogs, you tell it's a dog. you can then build a classifier where you give it a picture and it will tell you if it's a cat or a dog. So that's obviously the first place to start when you're learning how to apply this. So what we did was we said, okay, we want a material science problem. In particular, we want a problem in my structural domain. And what we specialize in is we specialize in this PDF. This is the pair distribution function technique, which is a way of measuring samples and then encoding the information as a list of interatomic distances, and then rebuilding the three-dimensional structure from this distance list. So the pair distribution function is a kind of a mathematical concept, but it's also an experimentally accessible quantity. So we developed ways of measuring this thing. Now, the question is, let's say I've measured a PDF from a sample. That sample might be a crystal. If it's a crystal, that sample has a space group. How do I just look at the PDF and get the space group of that crystal? Now, if I measure it using traditional methods crystallographically, there are ways of doing it. I know that I can get the space group by looking at the positions and the characteristic absences of all of the Bragg peaks. So if I have the Bragg peak information, I have a forward calculation. I know how to go from the Bragg peaks to a space group. When I make the PDF, it turns out that the PDF is just the Fourier transform of the diffraction pattern. Fourier transform is a linear transform, as we know, and therefore I'm not adding or removing any information when I do that Fourier transform. So if the information is in the diffraction pattern, the information is also in the PDF, but I don't have a forward calculation. I don't know how to go directly from the PDF to the space group. So this is like a classic example for a machine learning model. You're just going to train the machine learning model to do this forward compute that you don't know how to do. So we're going to build a machine learning model. The input is going to be the PDF, and the output is going to be the space group. And because we were dumb and didn't know any better, we decided to use a convolutional neural net because that's what's used for image analysis and that's what's used for cats and dogs, and we don't know any better. So that's what we did, and it worked. So this is the structure that we had. It was a rather straightforward off-the-shelf CNN, and the image that we gave it was actually the measured PDF. And this is the structure. I don't need to bore you with the structure. And then what came out as the output was the space group. It's a classification model. We published it in 2019, and it worked brilliantly. So we were off to the races. This is the top 6 performance. The top one is actually not a CNN. The top one is a logistic regression, which is not a deep neural net. So we were getting a 91% overall performance R1 score for a top 6 classification into 32 space groups. So it's actually working pretty well. The color of the space group indicates the crystal system. The size of the space group indicates we had a slightly unbalanced training set. So the large dots mean we had more things in the training set, and the smaller dots, these are space groups that are less heavily populated. And this is what the confusion matrix looks like. So we've got the true label on the left and the predicted label on the top. And if this was working perfectly, we'd have all 1s on the body diagonal and all 0s everywhere else. And it's working pretty well, but we actually saw these kind of interesting teardrops here. And these teardrops means that it's systematically misclassifying into a few space groups. And so the space group that it's misclassifying into is P21 upon C. And this is this one. And also P bar 1, P1 bar, which everything is P1 bar plus additional symmetry. And this P NMA. And it turned out that actually this is a kind of a known problem in indexing, which is there's these subgroup relationships, and you can often misclassify something into a supergroup of a subgroup. And so that's why a lot of this is happening. So that was pretty cool. We were happy with that because actually we were learning physics or learning crystallography actually from the machine learning model. by learning where the machine learning model went wrong. So that was nice. We were happy with that. Okay. So we got to start to get greedy then. Like, okay, we did the classification one, which is cats versus dogs classification. Why don't we try and go for the facial recognition problem, right? So the facial recognition problem is not classifying into a cat or a dog. It's recognizing the actual individual, the actual particular, my dog. And so that the PDF equivalent of that is we're going to give us an input, the PDF, and get us an output, the actual structure of the material. So we're going to try and do structure solution using neural networks. So now what I knew at the time was that these models are kind of doing interpolation. So the basic approach with a Gen AI is that you find a low-dimensional embedding space or a low-dimensional latent space, and you train a model to map the high-dimensional object into that low-dimensional space, and then you decode from that low-dimensional space to the high-dimensional space again. This is not how all Gen AI works, but this is a very kind of general way that we can think about it. So again, I'm just an experimentalist learning machine learning. And so fundamentally, it's doing interpolation. And so I thought, oh, I was naive. I thought, oh, we need to find structures that can interpolate into each other. And one thing I know as a crystallographer is that I can interpolate FCC into BCC because these have different stackings. So FCC is a ABC stacking, ABC stacking, and BCC is AB. Actually, not BCC. This should be HCP. Sorry. It's AB stacking, and what I can do is I can introduce a stacking fault in here, so I can change that C to an A, and then that C to a B, and then I have a little bit of HCP embedded in my FCC, and I can add more and more stacking faults, and I can beautifully interpolate all the way from FCC to BCC. And since machine learning models are doing this interpolation, this seems like a good candidate. So we tried it, and this thing worked pretty well too. So this was done with Kirsten Jensen and Raka Selvin at University of Copenhagen. These are the students who worked on it. This is a publication, and this came out in 2023. So it kind of looks like this. Basic thing that we're going to do is we're going to start with a structure. We're going to map it into this low-dimensional latent space, and then we can unmap it. We can decode it from that latent space back to the structure. So nothing happened. We started with this thing, and we ended with this thing, but it made this journey through this low-dimensional space. And then what we can do is we can associate a PDF, a measured diffraction pattern, or a PDF with that structure. That means that we know, this is called conditioning, but we're like mapping the point in the low-dimensional latent space to this diffraction pattern. So once we've trained the model, what we can do is we can then use a measured diffraction pattern as a prior. We can take it here, then the model knows where to place it in the latent space, and then it knows how to decode from that latent space to the high-dimensional space. And so this is how it's going to do the generative AI. It's going to give us a structure it's never seen before by decoding a point in this latent space to the high-dimensional space. And so, as I said, it actually worked pretty well. This is what it kind of looks like here. And we can interrogate a little bit what it looks like. So the pink ones are all HCP variants. And so they're actually clusters, and they can look like this or they can look like this, but they're basically HCP-like. They have AB stacking. And then this pale blue color here, these are the FCC structures, these guys. And again, they can be octahedrally shaped or star-shaped, but they're fundamentally kind of FCC. And what we see is the pink ones all grouped together in the latent space, and the blue ones all grouped together in the latent space. And interestingly, they're separated by a bit. And here's where the interpolation is happening. These ones in between are orange, right? What are the orange ones? The orange ones are these decahedral structures here. What's a decahedral structure? It has a beautiful fivefold symmetry. And what it is it has these subdomains here, which are FCC. They're perfect FCC, each of these 5 subdomains. They're kind of tetrahedrally shaped blocks of FCC. But they have this twin boundary between the domains. This is actually an irrational boundary, but it's very close to a 1-1-1 twin boundary, which is actually basically this stacking fault. And so I would actually expect these decahedral structures to be in between the HCP and the FCC because they're stacking faulted HCP and they're stacking faulted FCC. So again, we're kind of learning physics from the machine learning model by interrogating what this space looks like. And everything is working exactly beautifully because I interpolate from this HCP to this FCC, and I find something in between. And what I find is this decahedral structure. So yeah, this is kind of cool, right? We're excited. We're very happy with this. We're learning about machine learning, and we're learning generative AI, and we're learning about how it works. We're learning a bit of mathematics along the way. So then we're kind of like, well, actually, I don't want to just do close packed clusters, because although that's cool, it's not useful for anything. What I really want to do is I want to look at things which have chemistry. So I want to say, I want to predict something that's sodium chloride or calcium carbonate, right? But if I fundamentally know that I'm doing interpolation, like how do you interpolate from sodium chloride to calcium carbonate? You simply can't do it. You can't take these atoms and rearrange them and get these atoms. There's no way to interpolate because we have this kind of categorical change in the chemistry. But what we can do is we can actually find a different featureization. We can encode the information differently, and we can do it in terms of electron density. So all we have to do is instead of like putting atoms in the box, we can just put electron densities in the box, right? And if you have a heavier atom, you have more electron density. So this was our follow-up. This was done with a collaboration with Hod Lipson, who's my colleague at Columbia. These are the students who worked on it, and this came out. It was also a variable autoencoder, CVAE. It had this structure here, but the main thing is that we were giving it as input a diffraction pattern, and we were conditioning it. We also had things that encoded some chemistry and encoded the position, but we were regressing an electron density. And our idea there was that we could then find anything in between sodium chloride and calcium carbonate by just moving electron density around. It's completely continuous space that we're working in. This one also worked pretty well. We only did 2 space groups. We did a high symmetry space group, and then we did 1 lower symmetry space group. The high symmetry space group worked really well. So this is ground truth in this left-hand column. And then this is what the model predicted in this right-hand column. So when it works beautifully. Again, all we're giving it as input is the diffraction pattern and the composition, the number of the atoms in the unit cell. And it's regressing this electron density distribution. So it's basically doing structure solution. I'm not sure if I have the ones that failed, but needless to say, some of them failed. Let's see. Yeah, these are some of the failures here. So this is ground truth on the left, and then what it predicted on the right. So it was having some difficulty. It was also very difficult to generalize it to like different space groups that were not in non-orthogonal space groups. At this point, I had a kind of a revelation, which is, yeah, these machine learning models are doing interpolation, but they're actually interpolating in the latent space. They're not interpolating in the high dimensional space. And so there's actually a way in principle that you can just come up with an architecture that you don't need to have, I was bringing too much kind of crystallographic prior knowledge to this problem. So why don't we just do it directly in this you know, why don't we go for broke and we'll say, okay, I'm just going to try and regress the coordinates of the thing, but I'll also have a way of predicting, kind of interpolating between the chemistry, but I'm interpolating in the latent space of the autoencoder. And the job of the machine learning model is to find that latent space, that low-dimensional manifold of the feature set that is interpolable. That's kind of what it does. So this is kind of the magic. And at this point, we became aware, actually, that diffusion models are really the way to go here. So we're going to make an autoencoder, but the part of it that does the kind of regression on the atomic positions is actually diffusion model. And this comes back to this MATTERGEN thing, because the model that we used was based on a CDVAE, which is crystal diffusion variable autoencoder, which was developed by the same group that did MATTERGEN. So this actually worked beautifully, and this paper came out in this year in Nature Materials, where we basically did the first kind of meaningfully accurate structure solution using this approach. And again, it works. This model builds in some known physics. So we know that we're looking for rigid units. So Vitaly likes to encode the physics by defining invariants. In these models, what you define, you make these models equivariant. So it's one approach would be to actually make your feature vector invariant, and then your model doesn't have to be equivariant. But another approach is that you don't force invariance on your input vector, but you make your model to be equivariant. Equivariant means that it's built into the architecture of the network that it doesn't, in this case, because it's SO3 equivariant, it's looking for something that looks like a rigid body, but it doesn't care about the orientation. But it doesn't have to learn that. That's built into the network. So we studied this, and we had a data set which had like 45,000 atoms in it, 45,000 compounds, and it worked brilliantly. This is the result, and we could really degrade the information content. So we could give it a diffraction pattern that you would get from 100 angstrom nanoparticle. So then your Bragg peaks become very broad and overlapped. We could even give it one where it was a 10 angstrom, 1 nanometer nanoparticle. So that would be like a cluster of a few thousand atoms. The diffraction pattern you would get from a cluster of a few hundred atoms even. And it was able to actually learn, predict the crystal structure from that in many cases. So this is really incredible. It's really powerful. It's working really well. And we had actually trained it, again, using our limited resources at Columbia on a data set of 45,000 atoms. I think 45,000, it might be 60,000, but anyway, that order of magnitude. In the meantime, what Microsoft did is they did the exact same thing, more or less on the same architecture too. So our model is called PXRDNet, but they had Microsoft money and they had a much bigger compute. And so they trained their model on a data set that was more than an order of magnitude larger. And what that does is it just makes your embedding space, your latent space, much richer, which means that it becomes what you might call a foundation model like GPT-3. It means that you can give it a prompt, not just on a very narrow topic that it knows about, but you can give it a prompt on anything and it will tell you something about that prompt. So the foundation model for materials is we can give it any prompt we want, which could be something about the chemistry, something about the structure, but it could also be something about the properties. And it will be able to give us back something that is, qualitatively meaningful. And that's because it was trained on such a large data set. And this hasn't been trained on these really large data sets, the DeepMind Genome one and the Meta one either. So in principle, in the next few years, I'm pretty sure that there'll be a new MATTERGEN that will come out. It's trained on those. So the future looks good. We're going to be able to do a lot of things with this. So one thing we immediately did is we said, here's this technique which called Zanes, which nobody uses for structure solution. Let's build a diffusion model and do structure solution from Zanes, and it works. So there's kind of lots of things that we can do. So kind of the summary about this is actually these models are really powerful, and you can give them anything and they'll give you the solution back. They're really like the ChatGPT of like materials structure, and they work. So what did I learn about materials from this then? So I gave you my whole history of like, oh, I learned this about how machine learning works, and I learned this, and I learned this. But at the end, what I realized is I'm learning something about materials that I didn't know before. And what I learned is that actually the structure of the problem, the diffusion models are going to work, but what they're going to tell you is either useful or not useful. And so the structure of the problem is really important. The input data is going to be something like a diffraction pattern or a PDF, and the output is going to be the structure. That's great. But when we start applying it more broadly, what does this thing look like? So when we train this model, we have to give it labeled data. So we have to tell it whether the structure was right or wrong. That's how we train it. That's how it learns the weights on its deep neural net, right? That means that we need to actually know the answer to this question of, it's going to give back a prediction. We need to be able to answer this question. Is that prediction right or wrong? That means that there's a concept of structure, that structure is categorical. That for a particular material, there's a right structure and a wrong structure. And what I believe is that fundamentally, this is problematic. This is not actually the way nature is. So let's actually kind of explore this in a bit more detail. So what's this? And Bethel is thinking about this as well. He has some great ideas, but we need a measure of success and failure that's categorical. And how do we do that? So if you go back to those massive data sets, the MATAGEN was trained this way. I think probably that some post-processing was done for the DeepMind one as well. How did they assess whether the structure is right or wrong? And how do we assess when structures are the same or when they're similar, right? So again, this is something that Vitaly and his group have talked about a lot. So in the MATAGEN work, they have this concept of a SUN material, which SUN stands for stable, unique, and new. And so new means that it's actually different from a known structure. So you have to have a way of telling whether, again, it's this categorical, is it the same or is it not the same? In other words, have I discovered a new material or have I not? So how do they actually do it? And it turns out that there's this one measure which is like sitting around on the internet that they all use. It's called Structure Matcher, and it's part of the PyMatGen package. And the reason they all use it is because it's in Python and it was built as part of the materials project at Berkeley Lab. And it's really easy to use, and it behaves in the right way. You give it a structure and it tells you whether you give it two structures and it tells you whether they're the same or not. But as far as I can tell, it's not been heavily validated. Like nobody in the materials science community has actually done the hard work of saying, is it actually getting this right? And so we're basically taking on blind faith that this metric that they're using to train their model is actually the right metric. What tends to happen is that these predictions predict millions of new materials, and then chemists come along and they point out all kinds of problems with these. So there's a bunch of papers coming out where the chemists actually look at what was done. This is one example from Tony Cheetham, who's a very well-respected chemist, and Ram Seshadri, his colleague. Actually, these are my new colleagues at UC Santa Barbara. And they basically kind of show that their critique was on the A-Lab paper, which was a high throughput paper that also from Berkeley, but they kind of show that all of the materials that those guys claim to have found were basically not really novel materials. So we've really got this kind of problem that we have these super powerful models, but we don't have a good definition for the task that we're training the models to do. So I think this is a really interesting kind of fascinating thing. And it made me think about actually what is a structure. So we want to ask the question when two structures are the same. We want to know when they're similar. We want metrics to do this, but we also need to have a definition of what is a structure. Well, I'm a crystallographer. I'm a card-carrying member of the International Union Crystallography, right? And so this is what I immediately do. I go to the online dictionary of crystallography. This is our Bible. And I ask it, what is a crystal structure? And what it tells me is a crystal structure is a crystal pattern consisting of atoms. Okay, well, only a card-carrying mathematician could give a dictionary definition that looked like that. But of course, crystal patterns is clickable link. So let's click on that link. This is what a crystal pattern is. And a crystal pattern is an object in the n-dimensional point space, En, is called an n-dimensional crystallographic pattern, or for short, crystal pattern, if among its symmetry operations there are n translations, translation vectors, t, blah, 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 which are linearly independent. So that gives you the dimensionality. And then all translation vectors except the zero vector have a length of have a positive length, right? So it's basically, what's kind of interesting to me too is this is actually defining a crystal pattern as coming from a periodic system. And if you go and you look up at a crystal, it turns out crystals don't have to be periodic. But there may be a way around this because this is in an n-dimensional point space, and most of the non-periodic crystals, there are periodic versions in higher dimensions. But anyway, we're getting off topic of it. And then it says, when the crystal pattern consists of atoms, it takes the name of crystal structure. But this doesn't help me with my problem. I want to know what a crystal structure is, so I want to be able to answer I want an equivalence. I want to be able to answer the question of when two true crystal structures are the same or when they're different, right? And so this is a nice kind of rigorous mathematical definition, but, you know, for my purposes, essentially completely useless. So instead of asking crystallographers, let's ask chemists. So what about chemists? And chemists, I think, have a very crystal-centric view, and they all learned in their introductory chemistry course about space groups and the space group classification. And so one thing, they don't know when two structures are the same, but they do know when two structures are different. If the structure breaks symmetry, so it goes from one space group to another space group, then chemists will immediately tell you that those two structures are different. So they don't exactly know when two structures are the same, but they do know when two structures are different. It's of course possible in principle to have different structures that are in the same space group, but you know, that's something we don't have to discuss right now. So, but for me, this is like slightly problematic because I can imagine a scenario. Let's just do this scenario here. Thermal expansion. Let's say I have a cubic material and I warm it up. So if I warm it up, then it undergoes thermal expansion. Let's say that it expands isotropically. In other words, it doesn't break the symmetry when it does the expansion. Then the question is, has that structure become a new structure or not? If you ask the crystallographers, then I don't know who, it depends which one you ask, but I mean, in principle, all of the interatomic bond lengths have changed. Therefore, the structure has changed. If you ask a material scientist, I mean, they might argue it either way as well. But if the properties have changed, the material scientist will say probably the structure's changed. But if the properties haven't really changed that much, they say it won't. If you ask the chemist will say the structure hasn't changed. So because it hasn't broken symmetry, right? On the other hand, if the thermal expansion happens slightly anisotropically, so we're going to do what I call a minuscule phase transition, and that is maybe we'll take the same material as a starting point, and we simply pick one atom in the unit cell, and we move it off of a special position by a tiny amount. We've introduced a symmetry breaking change, and so the chemists will immediately tell you that actually that structure has changed. But if you look at the changes in the interatomic bond lengths, the change in that structure is much, much smaller than it is in the thermal expansion case. And so what we can have is a situation where the chemists will say the structure's changed, but the interatomic distances have changed by much less. So you can kind of see that it's a little bit of a mess. And what I like about this is that we invented crystallography basically 100 years ago, and we've been doing it for 100 years. And we've never really had this conversation until now, and we're having it now, or at least I'm not aware of it. And we're having it now because of actually machine learning being applied to crystallography. So there's another concept of isostructurality. So crystals can be completely different from each other, but considered isostructural. So the whole field is a complete mess. So this concept of isostructural crystals suggests that calcium carbonate, sodium nitrate, and iron borate are isostructural. And clearly these have completely different properties. They're constituted of different atoms. They have different intraatomic bond lengths. They're all completely different. So, just to say, I think this thing is a mess, and it would be great if we could, as a community, could kind of get this a little bit under control. So my time is up. I'm going to kind of summarize, but this is a plea to us as a community, and this means chemistry, crystallography, the mathematical community as well. We need more practical definitions for what it means for two structures to be the same or similar. Vitelli's work on structural similarity using invariance is really important. One thing that we typically do in the crystallographic world is we actually use this RW metric, so some kind of similarity metric between measured and computed structure factors. We have these tools here, so it's not like we're without tools, but I think it's an interesting conversation that we need to kind of continue. So I think I'm going to wrap up. This is a reference to a paper I wrote recently on the materials genome. I talked about this last year. It mentions Vitelli's invariance, but a number of other structural fingerprints, which are in the game for being kind of low-dimensional representations of structures. And a project that we're working on right now with my postdoc Tina and students Zoe and Andrew and other people in the group is actually looking at the similarity between similarity metrics. So these are just Pearson correlation maps. This one is a correlation map between, or what is this? This is basically a Pearson correlation between structures coming from the structure matcher. So we're starting to try and validate the structure matcher. This is the same Pearson map that we get for using pair distribution function as a similarity metric. And you can see it looks quite different from the structure matcher. Not completely different. I mean, it has in some kind of blocky way, it's similar, but this one is showing things in the middle here that are not really being seen as similar in structure matcher. If we look at Vitelli's metrics, or at least his favorite metrics from a year or two ago, this is actually, this is again a reproduction of the PDF one, and this is what his PDD is looking like and his AMD. So the AMD and the PDD give very similar measures of similarity to each other, but again, they're a little bit different from what the PDF is giving. And this is actually a correlation matrix between the similarity metrics. And so you can see that the PDF gives similar metrics to itself, and the PDD and the AMD give similar to themselves, but they choose different metrics to the others. to the other similarity metrics. And also, they don't all strongly correlate with the structure matcher, which is what everyone is using in the machine learning community. So here's the summary slide. Be careful what you wish for, because we have these powerful models now which will solve the problem. But because we have these, be careful what you wish for, because you probably will get it. And so we need actually better metrics that we're going to train our models on. And I like to use this quote, which I don't know, I kind of made it up, but the solution is not the problem anymore. In other words, solving the problem is not the problem anymore, but defining the problem is the problem. So I say the solution is not the problem is the problem. Kind of a mouthful, but yeah. So with that, let me wrap up. And this is a picture of my group just recently. So this is actually Zoe that I mentioned, and this is Tina. So this is Zoe, and this is Tina. And I think Andrew is not here in this picture. He fell asleep and he didn't make it to the group dinner. So, so yeah, let me stop. And I don't know, maybe I've run out of time, so there's no time for questions. But thank you very much, and I'm happy to take questions if there's time.
Thank you, Simon. Stop recording.